What's going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Today, we're looking at an example problem. We haven't done any example problems mathematically yet through this unit. And so I wanted to do that. We've discussed work energy theorem. We've discussed kinetic energy. We have discussed spring potential energy at this point. So I've got a practice problem here where we're going to kind of incorporate all three, or have the ability to incorporate all three. And we'll see how we can use our understanding of work or energy to go ahead and solve this problem. And there's two approaches, definitely. There's the work energy theorem, which we've been relying on a lot. And there's also a conservation of energy theorem we can use, or a law of conservation of energy that we could use, which we haven't done a lot of yet, but we certainly can. And so we certainly may. But I'm going to start off with the work energy theorem. So here's the problem. The problem is I've got a box loaded up on a spring, a very strong spring, a 500 Newton spring, or Newton meter spring. The box is 20 kilograms, and it compresses that spring by a distance of 0.5 meters. I can now find the force on the spring acting over there, which is great. And then I go ahead and I look and I see that there's a surface of 3 meters, or a space of 3 meters where there is no friction. So this box basically gets launched off of this spring, and eventually it reaches a rough patch. And at that rough patch, we see that the coefficient of friction is 0.5 meters. I'm sorry, not meters. There's no unit on coefficient of friction. But we have the rough patch. And our job is to figure out how far over that rough patch will the box slide before it comes to a stop. So this is our task here. All right. I wonder where we should start. Where should we start? I guess we labeled it, right? We have three scenarios. We've got A, B, and C over here, where we see A is the point where the box is loaded up. B is the point when the box has finally left the spring. Now it's moving. I should see work from the spring going into kinetic energy. And then over here at point C, we've seen all that energy dissipated because it's come to a stop, and the work of friction has removed the kinetic energy and brought that box to a stop. So what I want to do is think about my system. And in order for us to think about this system, I want to think about the forces that are done on the object. So at my initial spot, if I go ahead and draw my FBD, here's the box. There is a spring force acting on it. It certainly is. And then over here at point C, there's going to be a force of friction, kinetic, acting on it. So when I think about myself trying to figure out which of these methods will work the best, I need to think about where is the energy initially, what is my system. And so for this problem, springs are weird. Springs do not offer constant forces. They change. That's what our spring lab told us, right? As things stretch or compress, forces change. So it's really difficult to use this equation. The work done by the force of a spring equals force of a spring times the distance it acts over. That's really tough to use because the force changes. So when I'm using algebra alone, this equation does not work, because if I think about, as this box moves closer and closer to point B, the spring force actually decreases. It's a restoring force. It decreases as it moves closer and closer because of the nature of the spring force. So I actually can't use work of a spring in our traditional sense. So because of that, let's include the spring in my system. Let's say my system, in this case, is going to be the spring and box system. And if this is the case, let's go ahead and label the energies that are present at different points from A to B to C. So let's do that. At point A, the energies that are present are potential spring energy. There is a spring, it is loaded up, there is potential to push that object. This is the energy present. It's not moving at point A, so I don't have any kinetic energy. I just have US. Could there be gravitational potential if we got to that point? Maybe. I mean, we're above the surface of the Earth, but across this problem, we're not seeing a change in height. So I wouldn't even use that if we were talking about it, but we're not. So if you don't know what I'm talking about, forget the last 10 seconds. At point B, the spring has completely pushed back to its natural length. The box has left the spring. Now the box is moving. That spring force has caused the box to move. So within my system, all of that spring energy, that force of spring, has been converted over into kinetic energy. Now the box is moving. So now the box spring system has converted energy over into kinetic energy, or potential spring into kinetic energy. This is an example right here of conservation of energy, where a force that is inside my system, and because the spring box is my system, the spring force is within my system. Internal forces will cause transformations of energy. They will not cause changes in value. So this internal spring force that acts on the box within my system converts, transforms potential spring energy into kinetic energy. This is an example of the law of conservation of energy. It's just something we haven't covered, but I'm planting a seed for you to think about as we get closer and closer to discussing that more closely. At point C, we've come to rest. We have come to a stop over at point C. And if we've come to a stop, the energy stored in the spring box system is actually 0 joules. It is not moving. There is no spring compressed on it anymore. So there's no energy at the end. This is an example from point B to point C where work has caused a change in energy. This is our work energy theorem over here. So I see a conservation of energy early on, an internal force causing a transformation of energy. But then from point B to point C, I see an outside force, the force of friction over my rough patch over here, causing a change in energy. And my job is to figure out how far the box travels over the rough patch in order for the box to stop. So I'm going to look here. Now, I don't actually know much information about how the box works, but I do know that all of my initial energy is in the spring. I do know that it converts over to kinetic energy, but it's initially in the spring, and eventually all of that energy is dissipated over the rough patch. So I can start to generate an equation. I can go ahead and say, well, the energy at point A is equal to the energy at point B here. And then at point B, as I move from point B over to point C, so these are equal values. So the US initially is equal to the kinetic energy. This is US at A, kinetic energy at B. These two values are equal, but then I know that this energy here, whatever it would be kinetic energy at B, eventually is acted upon by the work of friction, and because friction is in the opposite direction, the work value will end up being negative, leads to 0 joules of energy. This is from point B to point C. I have an equation that I am able to evaluate, right? I don't know, like I just said, much about kinetic energy, but I do know that kinetic energy is equal to the spring energy. So I can rewrite my equation. I can say that the spring energy at A plus the work done by the force of friction equals 0 joules at point C. Again, work is always positive until I determine, is it additional work, is the force and displacement or distance in the same direction, or are they in opposite directions? And then for opposite directions, I'll see a decrease in energy. So let's go ahead and start substituting in some variables, and let's see how my math works out. So potential spring energy is 1/2 times K x squared plus the force of friction times the distance cosine of theta. This will equal 0 joules. And because I know that I am moving in this direction, this is the direction of displacement, but the force of friction is back this way, cosine theta is going to end up being -1. So I'm going to go ahead right now and change this from a plus sign or addition. I'm going to remove my cosine theta and call this negative. It's -1. Now that I've identified force and distance are in opposite directions, I can go ahead and change that plus work to minus force distance. Those two vectors are in opposite directions, so it's opposite. All right, I'm looking for D. Do I know the spring constant? Yes, I know the spring constant. Do I know how far that spring was compressed at point A? I do. It was 1/2 meter. Do I know the distance? No, I'm solving for the distance of the work being done. Do I know the force of friction? I don't know friction explicitly, but I do know an equation for friction from previous units. So let's keep working through this. I'm going to go ahead and say 1/2 k x squared at A minus the coefficient of kinetic friction times the normal force. That's my fun equation, times D equals 0 joules. Do I know the normal force? Again, not explicitly, but if I think about my forces that are acting on the box, there's my weight force, there's my normal force. There is no acceleration in the vertical direction, so my normal force must match my weight force. Weight force is always equal to m baby g on the surface of this planet. So I'm here with 1/2 k x squared minus the coefficient of friction mg times distance equals 0 joules. Here is my basic setup. At this point, we've gotten to our algebraic answer. We don't have a numeric answer, but we have an algebraic setup where I can solve this. Pause it here, plug in your variables, determine the answer. What is the distance this box will slide over the rough patch? When you're done, come on back and I'll have an answer for you, all right? If you're back, let's find out what the answer is. I'm gonna grab a calculator. As I go ahead and I algebraify this thing, I'm sliding the board down here so I have more space right here. What I end up seeing is that the distance is going to be equal to, add it, divide it, I'm going to get k up here, x squared over 2 times mu mg. D equals this. I've added this value over here. I've divided by mu mg. I ended with kx squared over 2 mu mg. And let's go ahead and start plugging some things in. This is a 500 newtons per meter spring. It is displaced 0.5 meters. Make sure you square that over the 2 from the 1/2. Coefficient of friction is 0.5. The mass is 20 kilograms, and at the surface of our planet, baby G is 9.8 meters per second squared. Let's go ahead and solve this. Check your answer with me. The distance covered is 500 times 0.5 squared divided by 2.5, 20, 9.8. Does my answer make sense? If my answer is a super big 30 meters, that doesn't make a whole lot of sense. I end up with 0.637. We'll call distance 0.64 meters. How far did the box slide? It slid 0. It's hard to see. 0.64 meters. How did I do it? I looked at my problem. I defined my system because the work of the spring is confusing. I defined my system as the spring and box. I looked at the energy present at what I considered 3 critical points. Initially, after the spring was released, giving it speed, and at the end of my problem down here when the box came to rest. I looked at how those energies would look algebraically, where spring energy equals kinetic energy as the spring releases. And then I looked over here at where work is done on my system by an outside force, friction. I made a quick substitution, and the rest of this is algebra. I would say that all of this stuff up here largely is the physics. And aside from just these quick 2 substitutions, the negative down here for cosine theta, and the substitution down here for mg in for Fn, aside from those things, from like here down is algebra. The physics exists up and over here. Real physics concept heavy, down here is algebra heavy. So if you struggled, figure out where you struggled. Was it with the concept? Was it with the math? If you have questions, as always, drop them in the comments or ask me in class. Until next time, see ya!